country, and here in Melbourne, the Wurundjeri people of the Kulin Nation, and I pay my respects to their elders, past, present and emerging. Our present today is going to feature research from Geoscience Australia, and we'll get to that in just a moment. But for those of you who don't know me, I'm Andy Gledo. I'm an emeritus professor at the University of Melbourne and one of the node leaders in the AuScope Geochemistry Network. Move on to the next one. I'm just going to briefly explain again what the AuScope Geochemistry Network is. It's a group of laboratories around the country that are aiming to create a national network of geochemical labs that contribute data to central and fair repositories, enabling researchers to solve the national challenges of today and tomorrow. That's a sort of a nice little statement of what we do. The personnel, the people involved in the development team are based at Macquarie and Curtin and Melbourne, and a number of people, but the ambition for this whole project is to involve many different labs around the country. This is just in the early stages and developing the AusGeochem portal. Today's talk, however, is from a different perspective from the survey from Geoscience Australia, and we're going to hear from Geoff, Fraser and Kathryn Waltenberg about an Isotopic Atlas of Australia. So without any further ado, well, no, actually, I'll just introduce them. Geoff is currently Director of Geochronology and Stratigraphy as part of the Mineral Systems branch at GA. He obtained his honours degree from the University of Adelaide, where he was very much influenced and inspired by Mike Sanderford, who was there at the time. He did a PhD at the ANU under Ian McDougall and Dave Ellis, investigating fascies metamorphics from East Antarctica. He then had postdoc positions at Adelaide and in Calgary before joining Geoscience Australia, where he's been for about 20 years, mainly working in applying geochronological methods to Proterozoic terrains. He's currently, as I said, Director of Geochronology and Stratigraphy in the Mineral Systems branch. Kathryn Waltenberg did her undergraduate and PhD studies in noble gas geochronology at the University of Queensland, and she's been at Geoscience Australia for 8 years. Is currently activity leader for age and isotopic mapping within the Mineral Systems branch in the Minerals, Energy and Groundwater division at GA. So to start things off, I'll pass over to Geoff Fraser, who will lead proceedings today. And I'll just say at the end, we'll have a Q&A session at the end. And if you'd like to join in with some questions, if you could please add those to the chat panel, and we'll attempt to get to your questions at the end. So, okay, with that, I'll pass over to you, Geoff, to begin proceedings, and I'll stop sharing now.
Good. Well, thank you, Andy, and a big thanks to the whole AGN team for inviting us to talk to you today. So today, together, Kathryn and I are going to present an update on our efforts at GA to make age and isotopic data freely available and easily accessible to a whole range of users at the national scale and in general in map form. So at GA, we've been working on this for a few years, and we've dubbed it an Isotopic Atlas of Australia. And like any atlas, the idea is it'll have a range of different map types and derivative thematic maps as part of it. And as you'll see on this slide, as a sort of tagline to the Isotopic Atlas title, I've added this sort of line, foundational data for national benefit. And this is, I guess, just reflects the motivations at GA for why we've gone down this path and what we see the applications of age and isotopic data to be, or at least some of the GA's particular interests in those applications, and how we can, I guess, use that data to address various societal challenges that GA is involved in. I guess for us in geochronology and isotopes at GA, we see these just as one of the tools in a wide range of geoscience sort of toolkits, I guess. So we're going to give the presentation in two parts. Why am I not? Oops. Sorry. So I'll kick off here with an introduction and sort of a bit about the motivation for this work at GA. And I feel like it's worth being quite upfront about that sort of context, because the motivation for the work does to some extent influence the approach we've taken with it. And following that introduction and sort of the context for the work, I'll hand over to Kathryn, who'll give a bit more of a demonstration of the current state of the data sets and how to access them in the GA portal. But in very simple terms, I guess our motivations are to ensure that data are useful, usable, and used, to use this little sort of mantra that was a favourite saying of Richard Blewett, sort of former branch head here at GA. And I guess what this is trying to get at is that it's not enough, at least in an agency like GA, to generate data that's sort of theoretically useful. It's also got to be usable by others, and that means, I guess, in this context, probably means making sure the data are easily accessible and presented in formats and styles that people can use for the sort of applications they want, and even making the data usable is not really enough. In the end, the real test is whether it gets used. So those are the sort of things to keep in mind, or at least things that we need to keep in mind in the GA context as we do this sort of work. Okay, so why have we gone down this path with trying to generate an isotopic atlas? At one sort of simple level, I guess, it fits nicely with GA's some of our sort of corporate aspirations, and there's just a couple of snapshots out of GA's corporate plan, a sort of a decadal sort of vision for what GA's role is, and you'll see statements like these: that we will be the authoritative custodian of geoscientific data and physical collections for the benefit of Australians, and that we'll invest in developing data management systems, etc., to make those data sets available to address geoscience challenges. So at one level, that's I guess a mandate to do this sort of work. And so what are these sort of foundational data sets that we're talking about, and where does the Isotopic Atlas fit into that? So I guess one of the really most foundational data sets, I guess, from a geologist's perspective, is geological maps. And together with our state survey partners, that's something that GA has been involved in for many years, and we are still involved in refining and improving the map coverage of the nation or the continent. The main image you see here is a seamless surface geology map. It's produced collaboratively between us and the state surveys more than a decade ago. We're now well embarked on a program of developing a whole series of subsurface geological map layers, as you see here. And as an example, here's a relatively recently produced sort of basement map or pre-Neoproterozoic map of the North Australian Craton. So geological mapping, clearly a foundational data set. Geophysical coverages that many people will be familiar with. Perhaps we get so familiar with these data sets in Australia that we almost take them for granted, but there's an ongoing body of work required to keep these foundational gravity and magnetic coverages up to date and incorporate new data and level it into the existing grids and then re-release those. So that's work that goes on continuously in the background at GA. I was last week in Mount Isa speaking to industry geologists, and some of them made the comment that exploring in Australia is just so different to many other parts of the world because of the free availability of these sort of data sets. In many parts of the world, they're just not available, and that makes a huge difference in terms of what's possible here. Similarly, there's an effort going on to expand the portfolio of national geophysical coverages, and just a couple of examples here. On the left, AusLAMP, which is a magnetotellurics program to build a national scale coverage of magnetotelluric sites at approximately 50-kilometre grid spacing. and on the right, a similar effort with passive seismic that we call AusArray. So those data sets are already in progress and well on the way towards national coverages. Here's a couple of, well, an example from the I guess the electrical conductivity world, magnetotellurics, at a range of scales from a very coarse national model to regional scale in the top right to local or deposit scale. So these things again are getting increasingly used by our industry stakeholders. Here's another example from airborne electromagnetics. We're well on the way to a national coverage at 20-kilometre line spacing with airborne electromagnetics, and that's already by far and away the biggest AEM data set of its type in the world. And all of these things can be pulled together in various ways to create derivative products, such as this 3D interpretation, I guess, of the major crustal boundaries across Australia. So all fantastically useful data sets and products, which are getting widely used by ourselves and various stakeholders. So how does isotope age and isotopic data fit into this? So I guess a point that I often try to make is that all of those data sets we've just been looking at, the maps, the geophysical images, the structural interpretations, etc., are all representations of the Earth's crust in its current state. But we're generally trying to reconstruct or infer processes that happened way back in the geological past. In GA's case, mineralizing systems that might have happened 1.5 billion years ago, for example. So the only tool we really have for reconstructing a quantitative understanding of the timing and duration and rates of events back in the past is, as we know, radiometric geochronology and geochemistry. So here we have a real interest in maximizing the value of the data of that type that is available to integrate with our other geological and geophysical data sets to make the most sound interpretations. And I guess most people here are aware that isotope science has always been very much a sample-based and quite labour-intensive activity, and relatively slow and expensive in a sense, compared, say, to flying an airborne geophysical survey, at least in terms of the time required. And it's taken a long while, I think, to build up a sort of critical mass of data across the whole country that can be sensibly used at national scale in the same way that we use our geological maps or geophysical coverages. But I guess I would argue that now, as a whole isotope community, we are at that point where we do have critical mass of data, and it's now in our interests to draw out that collective value of the whole data set, and as well as recognizing the value of individual data sets at smaller scales. So you can see in the images here, particularly the one on the left, which is overwhelmingly based on uranium lead ages, a compilation of data at the national scale. I forget the exact numbers in this now. We know it's not fully complete with all the legacy data, but it's well on the way. I think there's something of the order of 4,000 to 5,000 data points here. So we clearly have enough data now to start seeing major patterns in the data, and to start even gridding that data to provide to sort of develop the sort of background contours like this to view the data in somewhat analogous ways to many of our geophysical maps. So this is, I guess, just not to undervalue the really specialist ways of looking at these data sets, like on Concordia diagrams or isotopic evolution diagrams, but I would also argue that depicting the data on these in this map view makes the sort of first order meaning of the data very widely accessible to non-specialists in isotope geochemistry. And essentially any geologist can look at a map and see patterns and relate those patterns to other things that they know about the area that they're looking at. And so those were sort of age coverages that we were just looking at. Here we've also now looking at other isotopic traces in the same sort of map views. So on the left, the near-dim model age map that many people will be hopefully familiar with. This is largely the work of Dave Champion and his co-workers over many years. The hafnium in zircon map, which is still a work in progress, not yet fully pulled together at national scale, but on the way. And on the right, a map of lead isotopes in ore minerals, largely the work of David Houston and his colleagues or collaborators. So those are sort of the layers that we've been working on so far. Kathryn will show you in more detail shortly. I just want to touch now on, so again, what did I mean when in my tagline about national benefit? So another part of the, going back to the GA sort of strategic plan, says things like, we will provide geoscience information to support new mineral and energy exploration technologies and drive new discoveries, and that we will stimulate exploration investment, including in critical minerals, to open up new producing provinces with over $100 billion worth of mineral endowment. So those are sort of aspirations or the goals. And so to give you a sense of how we're trying to do that sort of value add, this is an example of it's not a fact map, it's a prediction of the prospectivity for mafic magmatic nickel copper platinum group element mineralization across the country. It's based on geological data sets. It's not based on the known deposits. It's based on our understanding of that mineral system and the data sets that we can use to map that. So it makes a prediction of prospectivity. And I'll just point out that in that sort of red circle down in the southwest of Western Australia, it was predicting enhanced prospectivity in that region, and at least to some extent on the back of this map, a company took up tenements in that ground and has found the Julimar prospect, which is now regarded as one of the most significant new discoveries of that mineral type for many years. So these maps do have use and direct benefit for mineral exploration and discovery, and therefore value. This is just another example of the same approach, just to make the point that the map in the bottom in this case is a map of iron oxide copper gold prospectivity across the North Australian Craton. The sort of the image above the map is just to make the point that these maps are derived from a whole series of different geoscience data sets that are layered together as spatial views to map out the constituent parts of a mineral system and then produce the final map. So that the critical point here is that all the input data sets are essentially map views in order for this approach, for them to be incorporated into this approach. So if we want to incorporate our age and isotopic insights into this sort of approach, then we need to have the data in map views to be effective. So hence the Isotopic Atlas type approach. Here's just another example on a more regional scale of direct use of isotopes to guide mineral exploration or exploration ideas, strategies. So here we're looking at the patterns in lead isotopes in ores in the sort of Carpentaria zinc belt, up straddling the Queensland Northern Territory border. Again, the work of David Houston here. And the basic observation that David made was that the major deposits in the blue dots line up along a gradient in the lead isotopes. And that gradient is also found to correlate with a major gradient in the thickness of the lithosphere along that region. So that has led recently to some significant, I guess, correlations being made, and the use of that sort of gradient in lithospheric thickness as perhaps a potential guide to other places to look for base metal, sediment-hosted base metal deposits more broadly. So you can argue, and people do, about the model and the validity, but I guess the point I'm trying to make here is that we can use our isotopic data sets as an input into some of these mineral prospectivity type understandings and predictions of where to explore. So before I hand over to Kathryn, I also just want to relatively quickly just pay tribute to where we've come from and the people who've perhaps inspired some of this work. So as far as I'm aware, this work of Vicky Bennett and Don DePaolo perhaps the first published reference, I guess, to isotopic mapping. And this is work they did in the late 80s, mapping Western North America with neodymium model ages. So I think from memory, this whole map was based on 39 data points across Western North America. But you know, perhaps the first use of this approach in map form, and quite sort of visionary work at the time. And then perhaps a bit closer to home, I want to pay tribute to the work of Dave Champion and Kevin Cassidy in the Yilgarn in the, I guess, late 90s through the 2000s, where they developed this beautiful neodymium map of the Yilgarn craton that you see on the left, which highlighted some major fundamental, I guess, boundaries in the Yilgarn that could be correlated with near surface structures, and importantly correlated with different mineral prospectivity across the craton, which can be related to the progressive evolution of the craton. So that was a really influential piece of work, and perhaps the first use of isotopic mapping at that scale in Australia that I'm aware of, and was very influential here at GA, and led to the national neodymium map and where we're going to now. So that was sort of where we've come from in a sense. Just some quick comments on where we're going, perhaps more as a community in this sort of age and isotopic work. My top dot point there is just these are really just my reflections, but the top point is to point out that I think historically the main activity in isotopic geoscience has been data acquisition by researchers or groups of researchers in a particular problem or a particular region. So we're very good at that, and we have a lot of data because of that. I guess where we're going more recently, and you know, the AGN is a major driver of this, is putting more effort into data compilation and collation. I would say that in the past, I mean, obviously people have collated data at various times for various purposes, but it's often been a bit ad hoc and for a particular use, and then people subsequently have to come and redo it for their purposes. I guess we're trying to by generating these national coverages at GA, I guess we're trying to avoid that sort of repetition of effort. The third dot point there about data infrastructure, clearly things like the AuScope AGN portal are part of that, GA's portal, the various databases that underpin those things and enable portals to even exist, standard vocabularies, etc. So obviously effort has to go into that work for these maps to be delivered, or data sets. And then the final point is that you can compile data, you can generate data infrastructure, but there is still an ongoing role for data custodianship to keep those data sets and the infrastructure in good nick and working. And this is certainly something we've learned at GA over many years. And I think it's worth pointing out that we shouldn't, as a community, underestimate the need for these roles of data custodianship, both of physical collections as well as the data sets themselves. And that in many ways, or often, the sort of people who are skilled and dedicated to these custodianship tasks are not necessarily the same people who are most interested in the acquisition and vice versa. So we need to value people who are good at the custodianship and yeah, do a good job with that and have those skills. And we're lucky at GA to have some of those people, and I guess pay tribute to people like Simon Bedorkis and Kathryn, who you're going to hear from shortly, who have really played a key part in some of that sort of work. So with that's I guess the context of what we've been trying to do at GA and where we've, to some extent, where we've got to. What you're looking at here is a sort of a screen grab of the front page of the GA portal, where these age and isotopic data sets that I've mentioned are now available. You can view them in there, you can interrogate them within the portal, or you can download the data sets and take them away and put them in your own platform and do what you want with them. So at this point, I'll hand over to Kathryn, and she can demonstrate it I guess in all practical, sort of in practice, how to navigate through the portal and use the data in the ways that you might want to. So I'll stop talking there and perhaps stop sharing.
Thanks, Geoff. So,
second.
yes, I'm going to be presenting the risky part of this talk, the live demo portion. I'm feeling positive, but at the same time, I do have slides if I need them, if things go. So let me just pop the screen up. I've put a couple of links in the chat if you would prefer to follow along, because what I am about to be showing you is by and large publicly available right now. So I'm just waiting for my screen to settle down. Okay, looks good. All right, so I'm going to give you a quick tour of both the GA portal in general and also more specifically the Isotopic Atlas as it exists within the portal. And I just want to say straight up, I'm very familiar with this portal, and although I'll be trying to keep it quite simple, at times I'll probably be moving too fast to keep up. But if you're interested in learning more about how to use it, feel free to get in touch and I can take you through it at a different time. So hopefully now you can see the GA portal with the map of Australia in the middle. This is where we store a lot of and deliver a lot of data. So the layers tab on the left opens up and you can see a range of different themes for data. There is a lot in here. I would say at times it can be quite an overwhelming variety of data. You can see about halfway down now there's a Geochronology and Isotopes tab, and that's where we'll be looking. There's also, just for your information, there's also Geochemistry in here. I know this is the Geochemistry Network, so just thought I'd point out that there's hydrochemistry, inorganic, and a range of organic geochemistry data sets in here as well. They are by and large GA generated data sets and not compilations of external work, unlike the Isotopic Atlas, which does compile external data as well. So just checking whether I wanted to say anything else about this before I move on to, yeah, so for any of these data sets, you just click on a layer and then you can expand out and see the subsets of data. And obviously you're welcome to browse it at any time. But for now, because like I said, there's a lot here, I am going to move across to the second link that I posted in the chat, which is the Geochronology and Isotopes persona, they call it. All it is it's the same system, it's the same platform. It's just been designed with a focus on geochronology and isotope data. If that's all you're interested in, it simplifies things so you don't get quite so overwhelmed straight away. But all those other layers in the other portal are actually available through here as well. So you can see what's come up to start with in this portal. This is the point data for the geochronology that we have. And if you click on any of these little points, you'll get a pop-up and it'll run through all the different information that's attached to that point, that sample, that analysis. So there is documentation explaining all of these pieces of information are. Some of the hopefully more obvious ones are age in millions of years here, the uncertainty, the confidence, that kind of thing, all the kinds of things you might expect from an age compilation. And then there's a fair bit more metadata or supporting information about what type of geological event the age is describing, the isotopic system, in this case uranium lead, what mineral was analysed, for example the lab, the stratigraphy, any sort of rock information, the location, and near the bottom there's also a reference. So that's the original publication that the data comes from, and where possible there's a link to the actual, where you can actually read the report or the publication or the paper. In this case it's a GSWA survey geochronology report, and if you click on that PDF it'll take you just straight there. Others are DOIs, as you might know, links to the journal articles. Okay, I've picked a Northern Territory Geological Survey publication, but eventually I'll get to a paper and there'll be a link to a paper. So that's good. You can kind of see broadly what there is and look at it, but I know a lot of you are expert users in geochronology and isotope data and really just want to get your hands on it and do your own analysis on it. So it's like Geoff said, it's all downloadable. There is, when you go in here, the layers that are loaded are highlighted in a different color. This is the one that's currently loaded. This information button is where you go to download. There's a button here, download, and you can download things as CSVs, JSON, which I'm not super familiar with, but it's some sort of human and machine readable format, KML, which is used for Google Earth type things, and shapefiles for your GIS packages. Just clicked download the CSV just so that we have it. You can also, when I was talking to someone about this not too long ago, and I told them that we've got this portal where you can download the data, a comment I got was not another portal. And in a lot of ways, I understand that perspective because these portals all operate slightly differently. And if you're not familiar, it can take a long time to get up to speed. If you prefer to look at this data through a different portal or system, you can just copy this link. That's the link to the web service and import it into your own portal or GIS system that way. So yeah, I will open this just so that you can have a look at the kind of tabular structure. Basically, it takes that information that you saw for one single sample and it's in a big spreadsheet. But while that's loading, I might just go across to the next. So obviously the points on the map are coloured. There is a legend here. They're coloured in intervals of millions of years. But if you're still interested in just figuring out what the data actually is, there's a bunch of different styles you can apply. So geological events, what I mean by that is it representing igneous crystallization or metamorphic events, that kind of thing. There's a bunch of others, types of ways you can look at the data. For the moment, this geochronology layer, and I'll talk about the others in a second, is primarily uranium-led geochronology, with the expectation that we'll add a lot more data in the near future. So it's a little bit, well, it's extremely biased towards uranium-led data. So all the pink spots are uranium-led data points, and everything that's not pink is something else. But there's only a handful in the middle of Australia, and I mainly added them just to make sure it would work. Yeah, so I mean, I can keep going through. There's filtering options. You can, restrict your search to samples of a certain age, that kind of thing, and you get a subset. Probably going to have to speed up a little bit, but anyway, basically, it's got search functionality and that kind of thing. And when you filter it down, then your download only has that data in it. What else did I want to say before I move on? Okay, so that's the basics of what you can do within the portal. I also showed you how to download the data. Like I said, that's the geochronology. We've also got subsets to help people find subsets they might be interested in. We've grouped it into, instead of something like the isotopic system, like uranium, lead, or argon, we've grouped things into igneous, sedimentary, and metamorphic related processes. And just while it's here, I'll also point out that some of the state and territory geological surveys also have geochronology and isotope web services, and they are also viewable through our portal. I will say that generally you get better functionality when you view these web services in the platform they were designed for, but at the same time, it still gives you an idea of what's available. So isotopes. This is a similar concept, but executed slightly differently. I should mention that the geochronology we were looking at were summary ages. They weren't the full analytical details of every spot analysis, for example, or every step in a argon heating experiment. But these isotope data sets are different in that they do preserve the detail to the limit of the analysis. That's not as important right now for the neodymium and the lead-lead isotope data sets because they are predominantly whole rock analyses. So one rock, one result, one row in the table. And here you can see this, the neodymium coverage, for example, and it's downloadable in the same way using the same method. But for hafnium in particular, because so much of it has been done by laser ablation on zircons, and you get multiple results per sample that you need to interpret together, we have a summary layer which gives you a quick visual idea of what's going on. Pretty basic kind of, it's mainly for like viewing it and getting an idea of what's happening. You can download this as well, but it doesn't have the full system. That's in the summary layer, but we have a complementary full analytical data layer, which actually, if you download that, you'll get every 20 or 30 analyses for each sample, plus all the standards and that kind of thing that were reported along with those. So although the lutetium hafnium layer is not as spatially extensive, it is just as large in terms of the data that it's storing because there are multiple results per sample. Okay, so the things I've just shown you, I probably should have mentioned this a bit earlier, but another good thing about going specifically to the Geochronology and Isotopes portal is that in this About button at the top left, there's a little help file. I need to make it more obvious, but it is there. I'm going to fix this. There is a little, what's the word, link here. If you click there, it downloads a document that tells you how to go about doing the things that I was just showing. So that's another way you can get help if you need it. So that's great. That's the data. We also have tools to visualize and plot things and make it easier for people who might not have access to the very specialized plotting software that you need for this. So there's an isotopes and geochronology tool set. I think that it's not working right now, which is unfortunate, but what I will do, that's a very temporary thing, but that's always a risk of these live demos. So I'm just going to hop quickly back to the GA portal and pull up the entire list of tools and instead show you the geochemistry, inorganic geochemistry plotting tools, just to give you a little bit of a flavor for what we can do. So here's the inorganic geochemistry data set. Just zoom in a little bit. So there's a number of ways to search for data. I'm just going to do this really quickly. I'm just going to draw a box and search. And it pulls up all the results. In that box, there's 230 geochemistry results. And then there's statistics and stuff, but I think the graphs are much cooler for me personally. So these are some examples of kind of, they're not just XY plots, they've also got, some guidance on what they mean. I'm just going to go across to classification diagrams and show you. So, we have these diagrams with the points plotted on the map and a little bit of extra information in the tooltips, and then some curves and that kind of thing. And we're implementing heat maps as well, because one of the problems with sometimes you get with this data is the outliers look really visually strong, but in reality, most of the data is, in this case, clustered down the bottom left, and the heat map kind of draws that kind of thing out. So I think that's a really useful addition. So yeah, it's unfortunate I can't really show you live what the geochronology equivalents look like, but I will just very, very, very quickly show you some examples just in the PowerPoint. So there's things like this plot here on the right. I hope you probably can't read what it says, but it's a histogram. Age is on the x-axis, and then number of results is on the y. So it's basically, yeah, it's a histogram of the age distribution in this selected area. Yes, and so we also have a different way of plotting. It's kind of time-space plot-like. So age is on the vertical, and then things are grouped into igneous crystallization ages and various across the plot. So everything in here is an age result. So for example, let's find an easy one. So this one is about 300 million years. It's an igneous crystallization age. If you hover over it, you'd get information of what that actual sample is. It's, what's the word? Stratigraphic unit and the lithology and that kind of thing. And then the little coloured bars around the outside are the error bars. So some of these have higher uncertainty and they're shown. So there's things like that that just help you at a glance quickly assess what the data looks like before you download it. There's similar things for lead isotopes I've got here. Lead isotopes, this is, 207 on 204 lead versus 206 on 204 lead. The data points are all plotted, and then there's the Stacey-Kramer's evolution curve. And it's a drop-down selection, so you can change the evolution curve if you prefer something different. For hafnium, you know, you get the epsilon hafnium or neodymium plots. If you're looking at neodymium, this is an example of, you can do the same plots on the summary data, which might be helpful if you're looking for broad trends, but if you want to plot everything you've got on the plot, then you can, and start interpreting it, start grouping it. In this case, the colors correspond to different classifications. So magmatics are dark blue, inherited crystals are in the greens, that kind of thing. So yeah, you get a little bit of a sense for what's going on with the data. I think that's, yeah, that's the tools. And then see if I can pull up. Okay, here we go. The last thing I wanted to talk about was the grids that Geoff spent a lot of time talking about. This is something that's not, it's so close to being implemented, but it's not quite there yet. I'm just looking for example, okay, this is the neodymium model age grid, so you can bring that in. You can also download these if you prefer, but I think the strength of these in the portal is plotting this on and then plotting other data sets like mineral deposits or something over the top of it and having a look around and seeing what you can see. I just want to make a couple of more general points. Those are the features. I know I covered them pretty quickly, hopefully kept up mostly, but so these data sets are not static, they're not complete, they're not done. We update them reasonably regularly. The system itself updates daily, although we're not quite that proactive. But if we spot errors or anything like that, we'll update them reasonably quickly. And we have ongoing releases and that kind of thing. For example, like I said, and Geoff said, there's a lot of data that's not here. This is mainly just uranium lead, and in particular places like Victoria at the moment don't have a lot of data, but we've got a pending release of about 900 ages, which will fill in that coverage. And similarly, there's a Tasmanian age compilation in the works to add to this as well in the coming months. Similarly for the other isotope systems I mentioned, but we also want to add additional isotope systems. There's a lot of interest in strontium isotopes and rubidium strontium data at the moment. Radium osmium and light isotopes are the things we're thinking of. We also have a complementary data delivery system that predates all of this, which is our Geochron delivery system, which delivers our in-house shrimp uranium lead data. That is the full analytical data set. We are going to bring that system into here so you can download that data through the same portal as well. And we are aiming to also expand that so it can store uranium lead data from any type of analysis, you know, like laser or TIMS as well. So those are kind of the ambitions for the next few years, as well as giving you an overview of what currently exists and the kinds of things that you can expect to see in the near future. So hopefully I've left enough time for a few questions. That's all I really wanted to cover, but if there's anything else anyone wants to know about, please ask. Thanks.
Thank you very much indeed, both Kathryn and Geoff. Outstanding.